All right, now we're looking at speed time graphs right now. And now we have looked at a different type of graph before, but that was a distance time graph. And when we found the slope of it, we were able to find the velocity. All right. Now for us, we can also use a speed time graph to find the slope, or if we do find the slope of a velocity or a speed time graph, we can find our acceleration. So if you have a distance time graph, you find the slope, you can find the velocity. And if you have a velocity time graph, you can find the acceleration. And so when you have acceleration means there's actually slope. So somewhere on my purple line here, when we have any kind of a slope, whether it's positive or negative slope, that means you have some acceleration happening. You have a change in velocity. But as you can see it in red, when the velocity is steady, doesn't change, well, then there is no acceleration, because acceleration, again, is all about a change in velocity, either in terms of magnitude or direction. But generally, when you have a graph, you're not going to have a change in direction. But it can happen. All right, now we're going to look at the differences between a distance time graph and a velocity time graph. So you can see here, time is both on the x-axis of both, but on the y-axis, well, we have distance for a distance time graph, and for a velocity time graph on the y-axis, we have velocity. Now, the one thing is that we've got a three different scenario here. Constant speed, which means you're constantly going, say, like 80 kilometers an hour. You're stopped, or you're changing your speed. So we're going to look at the three different scenarios and just kind of how those graphs would look. Now, if you have a distance time graph and you have a constant speed, that means you're going the same velocity, and so your still distance is increasing. But here's the thing, it's a nice straight line, although I know mine isn't, because I'm drawing with a mouse here, but it's a nice straight line. Now it can be sloped differently. The higher the slope, the faster we're going, because again, the slope of a distance time graph represents our speed, and so the higher the slope, the higher the speed. Now, if you're going at constant speed, our velocity time graph is going to look a little bit different, or our speed time graph. So say we do have a certain speed, I'm going to say right here, we're going to start off with this speed, whatever it may be. And if it's constant, it means it's not going to change. And so we're going to have a straight line right across, because we're constantly having the same speed. All right, so there's a difference in the two graphs for, again, the same situation. All right, now, again, here's another situation where something is stopped. So let's say that it traveled, I don't know, this distance right here that I marked in blue. All right, so that's how far away it is from wherever it started. But because it stopped, its distance does not increase. And so that is a situation where our line goes flat across. Now, in terms of our velocity time graph, well, if it stopped, that means you have no velocity. So you're down here. And as you go along, well, we're going to have another straight line. But in fact, this one has to be along the bottom because our speed is 0. It stopped. All right, now our third situation is when we have acceleration. So that'd be like going starting from a stop sign, and you press the gas, and because if you look at the speedometer in your car, the velocity is constantly increasing. You're accelerating. And so in this case, your distance, say we're crawling from a stop sign, is increasing, but then your speed's increasing, so your distance is increasing even more and more. And so in fact, we get a line that's going up, but it's not straight. It's in fact curved because the velocity is changing. We don't have a nice straight line. Now, where we will get a nice straight line is a speed time graph, because our speed is constantly increasing. So again, I'm going to look at the perspective that we are at a stop sign. So given what I've seen in a high school parking lot, I'm not going to put the velocity at 0 because I don't see too many of you guys stopping for stop signs, but you should. All right. But you, again, we'd have a nice line here and your velocity is constantly increasing because you're accelerating. Now, you notice I didn't draw the line like this. I've had a black truck, one of my, at the school I was just at last year, and I think that's how that person left the school parking lot every day. But no, a nice flat line here. But again, the velocity is increasing as you're accelerating. All right, now we have it. There we go. We're going to work with velocity time graphs. And what I want you to look at is that we're going to find the acceleration because, again, if we find the slope of a velocity time graph, that's another way to get the acceleration. So earlier today, we could find acceleration from using a formula. Here, we're going to use a formula, I guess, because we're going to use slope. Again, a little grade 9 math, rise over run. That's what we're going to use to find acceleration. So A here starts off with, what is the acceleration of the object between 0 and 2 seconds? So here's 0. And let's see, so that's 4. So I guess halfway here is 2. And so when we are finding the slope, so A, find acceleration, is going to equal slope. And again, as I was saying, we're going to use a little grade 9 math of rise over run. And so in this case, for 2 seconds, there's our run right there in blue. So I'll put that down here, 2 seconds. And then the rise is how much you go up. So I go up and I look, and that green line has a height of 8 meters per second squared. I don't really need to put the units in here until the end. And so the acceleration for this object between 0 and 2 seconds, well, if I take 8 and I divide it by 2, I'm going to get 4, and that would be the units, again, are meters per second, or short formed it to meters per second squared. All right, now the next one is, what is the acceleration of the object between 2 and 10 seconds? All right, so again, I'm going to use my rise over run here. So let's see here. Let's erase this. All right, and so from 2 seconds to 10 seconds. So there's my 2 and there's my 10. Now, I look at my line here and it's a flat line, totally flat. So you either have negative or positive slope. It's not going uphill or downhill. And so in this case, again, our acceleration, which is equal to slope, well, if you got yourself a flat line, it's 0, right? It's a flat line because I should put as our velocity, we had velocity, it just did not change the whole time. And that again is to do with acceleration. See, at from 2 seconds to 10 seconds, this person was going 8 miles or meters per second. Never changed. So the acceleration is 0. All right, then we get to the next one. What is the acceleration of the object between 10 and 12 seconds? All right, so again, I look at 10 to 12. All right, I'm going to look at the slope. So again, I look at the run. So I'm going over. That's my purple line here. And so I guess I'm going to write this right here. I guess now I'll go back down. All right, so my rise or my run here is from 10 to 12. That's 2 seconds. And then my rise, which I really shouldn't call it a rise, I'm going down. So it's more of a drop. And I'm going a drop of 8 to 4. So I'm going down 4. So my run is going to be over 2. And my rise, or lack of it, is going to be down 4. So when I find my acceleration, all right, so again, I'm going to use rise over run here. It's my slope. As I said, it went down 4, but it went over 2 seconds. And so if I calculate those numbers, take -4 and divide it by 2, what I have is -2 meters per second squared. Now, because it's negative, this is something I talked about in the first lesson today. We have some deceleration. The object or person, which I would call it a person, is slowing down. Negative acceleration. All right, so I go back up and look at the graph. Well, yeah, it went from between 10 and 12 seconds. We went from going 8 meters per second, whoever this is, and then at 12 seconds, they were at 4 meters per second. So they slowed down. Now, here's something a little extra, is the area. So we can actually find two things, pieces of information from a velocity or speed time graph. With a distance time graph, we could only find velocity, but with a velocity time graph or a speed time graph, we can find two things. And the second thing is that the area under a velocity time graph represents the total displacement that has occurred. So how far they've traveled. So what we can look at is, what is the net displacement between the times of 0 and 2 seconds? All right, so I go back up to my graph. Wish I could grab my graph here. See if I can do that. Is that possible? Ooh, I can do that. Let's bring this guy down. There we go. Get off there. All right, there we go. So if we want to look at from between 0 and 2 seconds, again, I'm trying to find a nice spot here where I can hide it. There we go. All right. So between 0 and 2 seconds, I want to find the area under the curve. Well, again, there's my 2 seconds right there. And so what we're looking at is the area of the shape that I'm putting in red, which is a triangle. All right, and so for D, if I want to find the area of a triangle, well, the area of a triangle, so I'm going to put, I guess, a capital A. We're finding distance, so let's put a D. It's going to be base times height divided by 2. That's the area of a triangle. And so in this case, our distance that this object has traveled in the first 2 seconds, we have D equals. The base is the distance along the bottom of the triangle, so I have a 2. The height of the triangle, how far up it goes from 0 to 8 here, so it's got a height of 8. And then I divide by 2. And if I do D equals, if I go 2 times 8, which is 16, and then divided by 2, well, I get an 8. And since our velocity is in meters per second and our time's in seconds, that means our distance is 8. So in total, in the first 2 seconds, this thing traveled 8 meters. All right, now we get to E up here. What is the net displacement of the object between 2 and 12 seconds? Down here to over here. All right, so we've got, I'm going to block it off here in purple. So we've got a couple different areas. We got one area here that I'll put as number 1. This object's kind of, I can go to nice rectangle here for number 2, and then a little triangle for number 3. So I got 3 different areas I'm going to calculate. All right, and so I'm going to do that up top here. Let's see, let's pick a different color. Let's go with green. All right, so the distance is going to equal. All right, so we have our first rectangle. Area number 1 here. Let's call that A1, I guess. Plus A2. Plus A3. These are areas I'm figuring out. All right, so if area, my first rectangle there, area of a rectangle is length times 1. Now, or length times width. So lengthwise, we go from 2 seconds to 10. So the difference there is, let's see here, 2, 4, 6, 8 long, and it's 8 high. There's the first area rectangle, plus we got our second rectangle here, which is 2 wide. All right, and how high is that for length or width, or however you want to say it? 4. All right. Whoops, 4, not 44. And then our last one there, we have a little triangle. So which again, I'm going to use base times height divided by 2. So the base is that little area along the bottom here, right there. So that's only 2 seconds, 2 seconds wide. So that's my base is 2. Height, it starts at 4 and goes up to 8, this little triangle. So that's got a height of 4. And then, of course, I have to divide by 2. All right, so now I just got to figure out my total area here. Add them all up here. So 8 times 8, 64. Guys, it can escalate quick. That's what happens sometimes. Let's see, 2 times 4 is 8. And then the other stuff. Let's see here. So 2 times 4 and then divide by 2. Well, 2 times 4 is 8 and divided by 2 is 4. And so if I add all those up, let's see, 64 plus 8, that's 72. And then plus 4, well, we get 76. And again, our units have to be in meters. Meters. Oh, cap lock off. Meters. There we go. Because again, our velocity is in meters per second and our times in seconds. So that means our distance has to be in meters. So again, we can find two things with a velocity time graph. We can find not only acceleration, but also the distance. All right, so let's check out example number 3. I'll check the chat here, see if there's any questions. Don't we divide by 2? I did do that. I did do divide by 2. You can see it up there, green. There's my little /2. So 2 times 4 divided by 2. There was only one triangle. Number 3, area number 3 was a triangle. Little 2 here is a little rectangle. 1 was a huge rectangle. All right. Now, let's see. We get to the next one up here. All right. So I'm going to shrink this up a bit. Easier to see. There we go. All right. An object starting from rest moves north with the following velocities. All right. So we got time here and we got velocity. And so we're going to have to graph the information first on the graph. So let's see here. I got a graph. So I'm going to have a 0. Now, when you have a table of values, the y is always on the top. The x coordinates are always on the bottom. So time's going to have to go on the bottom here. And we're talking about seconds, standard units. All right, now let's see here. I got to go up to 8 seconds. I don't want this to be crowded, so I'm going to go with every 2 blocks is 1 second. I believe that'll fit. Let me make sure first. So that's going to be 1. That'll be 2 seconds, 3 seconds, 4, 5, 6, 7, 8. Yeah, they all fit. Okay, so 1, 2. So I'm just setting this up first. 4, 5, 6, 7, 8. That's all we know up to. All right, now over on the y-axis, we have velocity. There's actually some direction on it. It's not just a speed. All right, so it's velocity. Meters per second are our units. Nice standard units, good. And this is saying directed north. All right, now what's our highest number? We're starting at 0. It's good, okay. Our highest number is 40. All right, so when we get to 40, how are we going to do that? Let's see. I'm going to see if we can go up by 10s here. 2 blocks is 10. So 10, 20, 30, 40. Yeah, that's going to fit. So let's put that down there. There's 10. There's 20. There's 30 and 40. All right. Now we got to graph this information. All right. So 0, 0. Well, that's there. Not going very fast. We're starting from rest. 1 second, we're up to 10. All right. 2 seconds, our velocity is now up to 20. So as we're moving up here, you can see this thing's accelerating. We're going to have a slope here because it's increasing its speed, changing speed. 3, we're going up to 30. 4, we're going up to 40. Let's see here. Then 5, we're at 40. 6, we're at 40. So I'm just graphing the information here. 7, we're at 20. And then 8, we're at 0. All right, so there's our graph. I wonder if I got some nice lines here I can draw. Let's try that. Well, that's kind of aggressive line here. So I'm going to go with my normal line here. A little aggressive. All right, so there we go. There's our graph. Whoop, that's terrible. Let's get that fixed up. There we go. Nice straight across. And down we go. All right, so there's our velocity time graph. All right. Now we get to the questions. Let me move that up. A few of them up here. Whoa, we got stuff way down there. All right, let's start with this too. What is the acceleration of the object between 0 and 4 seconds? So again, because this is a velocity time graph, we can find the acceleration by, again, finding the slope. All right, so we're going to look at the rise over the run. All right, so again, the run, if we're going from 0 to 4, there's our run. And so that's going to go down the bottom, and we've covered 4 seconds with that run. Now the rise, we go up. And how far did it go up? Well, we started at 0 and we go up and go across, and we've gone up 40 meters per second. And this one has a direction. This is a velocity time graph. Last one we had was speed. The only difference here is directions added. All right, so there we got 40 meters per second north. And so if I look at my acceleration, I take my 40 divided by 4, and I'm going to get 10. And again, my units are meters per second squared. This time I have direction, and that direction is north. And I just found it by finding my slope. All right, now the next one says, what's the acceleration between 4 and 6? All right, so we'll switch colors here. We'll go in purple. So again, I'm going to, well, I go up here. I look at my rise over run, but can somebody tell me what my acceleration would be between 4 and 6? Check the chat out. Nobody? Could do rise over run, kind of waste my time though. 0, yeah, we got no slope. All right, so our acceleration is equal to 0 meters per second squared. The velocity didn't change. All right, we have a nice flat line. No slope. Acceleration is 0. All right, now we get to the next one. What is the acceleration of the object between 6 and 8? All right, so again, I have to use my rise over my run. So I'm up here going from 6 down to 8. All right, so I go across and then down. All right, so I'm going over, let's see here, my run 6 to 8. Well, that's going to be 2 seconds right there. All right, and then I'm going down, let me see, from 40 down to 0. All right, so I'm going to find my slope again, my acceleration. The run was, again, 2 seconds. Put that in there. The drop was minus 40 meters per second squared. And again, we have direction on this one, so it's north. Now, if I divide my numbers, we're going to have to make a little adjustment here. I take minus 40 and divide by 2, and I get minus 20. All right, now I could write it like this, meters per second squared north, but this would be incorrect. I have to change it. That minus sign means we're actually in the opposite direction. And so what it really means is I've accelerated 20 meters per second squared, and because I'm in the opposite direction of north, that means we're actually accelerating south. We're slowing down. This thing was traveling north. It's slowing down, which means we're accelerating in the opposite direction. All right. What else we got here? A couple more. Displacement. What is a displacement from 0 to 4? So again, we got ourselves a triangle here. Might as well do D right here. Whoops, going red. D right here. All right, so we want our displacement from 0 to 4. Again, finding the area when we're finding our distance. And again, I'm going to find, I'll use D here, the area of a triangle, which is again our base times height divided by 2. All right, and so the base here, distance along the bottom is 4. Height all the way up to 40. And of course, we divide by 2. All right, and let's see here. Get my calculator out because I can do this all in one step. 44 times 40. Well, 4 times 4 is 16. Add a 0 is 160. We divide by 2, and I get 80 meters. It's traveled in total. All right. Then I get to E. Let's see here. Oh, Noah, did you have any questions? Oh, never mind. You're not here again. All right. So we get to E. Last one. Let's see here. It's down here somewhere. There it is. Way down here. What is the net displacement between the times 0 and 8? 0 and 8. So we got to find the area of this whole thing here. So it's getting a little messy here. I'm going to clean up this slope here. Let's get rid of that. So again, my blue. There we go. All right, between 0 and 8. So there's my blue line. Now we already found out from 0 to 4, so I can keep that 80. But what I can find out, so let's do that again. We're looking at, we already got our area 1 right there. From 0 to 4, that's a triangle. But now we got another 2 areas to figure out between 0 and 8. There's triangle or rectangle for area number 2. And then we have another triangle for area number 3. All right, so to find our distance for the entire duration of this event, switch color. All right, so we have D equals, so we got the 80. That's between 0 and 4. Now we have a rectangle. So again, length times width. So that rectangle is, well, 2 wide, because we're going from 4 to 6, so it's 2. But it is also 40 high. So there's our rectangle there, 2 times 40, length times width. And then we got ourselves a triangle again. So number 3, so it is, let's see, base times height divided by 2. The base of it is 2, because you're going from 6 to 8. The height, well, it's just like our rectangle. It has a height of 40. And then, of course, because it's a triangle, we got to divide by 2. All right, so our total distance, let's see here. We got 80. 2 times 40, well, that's also 80. And then we got 2 times 40, which I do know is 80 already. And then divide by 2, well, that's another 40 on there. So if we add all those up, let's see here. 80 plus 80. Yeah, Corey, I agree with you. 200 meters in total this person traveled. Even though it looks like they sped up, then maintained speed, and then slowed right down to nothing and stopped. But in total, that was a 200 meter journey. All right, so again, with a velocity time graph, there's 2 things we can find out. First of all, it's another way of finding acceleration, and also you can find out how far your object or the person traveled.